Far out beyond the orbit of Neptune, in the deep, silent freeze of the outer solar system, lies a realm of shadows and ice. This is the Kuiper Belt, a vast, donut-shaped ring of frozen leftovers from the dawn of our planetary system. It is a place of perpetual twilight, where distant sunlight is a mere pinprick in the darkness, and where ancient worlds, untouched for billions of years, hold secrets that can rewrite the textbooks of astronomy. And in this frozen frontier, one small world stands out as a paradox, a cosmic rebel that defies every rule we thought we understood. Its name is Quaoar. Pronounced Quaoar, this enigmatic dwarf planet is more than just a frozen rock tumbling through the void. For 2 decades since its discovery in 2002, Quaoar has been a quiet puzzle for astronomers. But recent observations have shattered that quiet, revealing a world of such profound and bizarre mysteries that it has sent shockwaves through the scientific community. What we are learning about Quaoar doesn't just add a new chapter to our solar system story. It tears out entire pages and demands we start again. It challenges the very foundations of planetary science, forcing us to question how rings form, how moons survive, and what forces are truly at play in the solar system's final frontier. In this video, we are embarking on a journey to the edge of the known, to unravel the 25 most astonishing unexplained mysteries of Quaoar. We will explore the impossible ring that orbits where it absolutely should not exist, a thin band of debris that defies the laws of physics as we know them. We will investigate its enigmatic moon, Quaoar, and the strange dance it shares with its parent world. We will probe the secrets of its surface, its composition, and its history, each clue leading to more profound and baffling questions. This is not just a list of facts, it is a detective story set on a cosmic scale, a deep dive into the anomalies that make Quaoar one of the most fascinating and important objects ever discovered. So prepare to have everything you thought you knew about the outer solar system challenged, because the story of Quaoar is only just beginning, and it is stranger than anyone could have possibly imagined. Our journey into the deep freeze begins with a mystery so profound it sent astronomers scrambling for their textbooks. The first, and perhaps most shocking, of Quaoar's enigmas is its impossible ring. In 2023, a team of astronomers pointed the powerful European Space Agency's Cheops Space Telescope, along with other ground-based instruments, toward Quaoar as it passed in front of a distant star. This event, known as a stellar occultation, is like a cosmic ultrasound for distant worlds, allowing scientists to probe their atmospheres and surroundings by watching how the starlight dims. They expected to see the clean, sharp dip in light caused by Quaoar itself. What they saw instead was a series of smaller, brief flickers both before and after the main event. These flickers revealed something that should not be there, a thin, dense ring of particles encircling the dwarf planet. Now, rings themselves are not unheard of. We have the magnificent rings of Saturn, of course, and the fainter rings around Jupiter, Uranus, and Neptune. But every single one of those rings exists within a specific, crucial boundary known as the Roche limit. Think of the Roche limit as a planet's personal bubble of gravitational dominance. Inside this zone, the tidal forces from the planet's gravity are so strong that they overpower the gravitational pull holding a moon together. Any large object that wanders inside the Roche limit will be ruthlessly shredded into countless tiny pieces, and those pieces will spread out to form a ring. It's a fundamental rule of orbital mechanics, a law of planetary physics that has held true for every ringed world we've ever observed. Quaoar's ring, however, is a cosmic outlaw. It resides far, far outside this gravitational danger zone. At a distance of over 4,100 kilometers from Quaoar's center, the ring is orbiting in a region where the physics textbooks clearly state that particles should not be able to form a ring at all. Out there, beyond the Roche limit, gravity is weak enough that the particles should have easily coalesced. snowballing together under their own mutual attraction to form a single, solid moon over a timescale of mere decades. The fact that they haven't, the fact that this delicate ring persists in this vast emptiness, is a direct violation of our current understanding. This leaves scientists with a monumental puzzle. What force is actively preventing these ring particles from clumping together into a moon? One leading hypothesis points to Quaoar's moon, Quaoar. Perhaps collisions between small objects within the ring, or gravitational nudges from Quaoar itself, are providing just enough energy to keep the particles bouncing apart, like constantly shaking a box of Lego bricks so they never snap together. Another, more exotic possibility involves the particles themselves. What if they are not made of hard, brittle ice like Saturn's rings, but are instead composed of a more elastic, bouncy material? Imagine a ring made of countless tiny rubber balls. When they collide, they might simply rebound off each other with enough force to resist sticking together. Yet even these creative explanations struggle to account for the ring's long-term stability. This isn't a temporary phenomenon. It's a structure that has somehow maintained its delicate balance for what could be millions of years. The existence of Quaoar's ring is not just a curious anomaly. It is a glaring sign that there are fundamental processes at work in the outer solar system, forces and interactions that we have not yet even begun to imagine, quietly defying the rules we thought were universal. This defiance of our expectations leads us directly into the second, equally compelling mystery, the peculiar composition of the ring itself. While its location is the headline, the ring's very substance may hold the key to its survival, offering clues written in ice and dust. Officially designated as Quaoar's first ring, and sometimes informally called the Weymouth ring after the location of one of the observing teams, this structure is not just in the wrong place. It seems to be made of the wrong stuff, or at least it behaves in ways we don't fully understand. What could these particles be that allow them to flout the laws of moon formation for such immense stretches of time? One prominent theory suggests that the particles within the Weymouth ring are not the hard, brittle chunks of water ice that make up Saturn's magnificent band. Instead, they might be composed of a much more exotic and resilient material. Imagine a ring not of tiny ice cubes, but of countless snowballs made from a strange, fluffy frost. This material could have a highly porous, fractal-like structure full of empty space. When these fragile, snowflake-like particles collide, they wouldn't shatter or stick together firmly. They would compress and then spring back, dissipating the energy of the impact in a gentle, bouncing motion. This fluffiness could drastically lower their coefficient of restitution, a scientific way of saying they are terrible at sticking together. It's the difference between throwing two clumps of wet snow, which might just splatter apart, versus two sticky mud balls that fuse on contact. If Quaoar's ring particles are these cosmic dust bunnies, their collisions would be soft and ineffective at building larger objects, allowing the ring to persist in its delicate, dispersed state. But the composition alone might not be enough. To maintain such a narrow, well-defined ring over astronomical timescales requires a shepherd, a gravitational traffic cop that herds the particles and keeps them in line. This brings us to another tantalizing hypothesis, the possibility of unseen shepherd moons. We know Quaoar has one confirmed moon, Quaoar, but what if it has more? Tiny, undiscovered moonlets, perhaps only a kilometer or two across, could be orbiting just inside or outside the main ring. The gravity from these miniature worlds would nudge any straying particles back into the fold, preventing the ring from either spreading out into a diffuse disk or collapsing inward. We see this phenomenon beautifully at work within Saturn's F-ring, which is sharply confined by the gravitational influence of the small moons Prometheus and Pandora. The search is now on for such a shepherd around Quaoar, but finding a dark, small object against the even darker backdrop of the Kuiper Belt is a monumental challenge for even our most powerful telescopes. Beyond gravity, there could be even more subtle forces at work. In the cold, near vacuum of space, electrostatic forces can become surprisingly significant. As these tiny ring particles are bathed in the faint stream of charged particles from the solar wind, they could build up static electricity. If particles develop the same charge, they would naturally repel each other, creating an invisible force field that keeps them at a distance. This mutual repulsion could be the very mechanism that counteracts their gravitational attraction, putting them in a perpetual standoff where they are forever pushed apart just enough to avoid coalescing. It's a delicate balance of forces: the weak, insistent pull of gravity versus the persistent push of electrostatic repulsion. On Quaoar's scale, this subtle tug of war might be the dominant physics, a hidden dynamic we rarely consider around the more massive, gravity-dominated planets of the inner solar system. The enduring puzzle of the Weymouth ring's composition and stability forces us to look beyond textbook gravity and consider a richer, more complex symphony of interactions happening in the silence of the deep freeze. While the ring presents a puzzle happening outside Quaoar, the third mystery takes us right to the heart of the dwarf planet itself, locked within its very spin. Astronomers have clocked Quaoar's rotation at a startlingly brisk pace, completing a full turn on its axis in just under 8.8 hours. To put that into perspective, our own Earth, which is significantly smaller and denser, takes a full 24 hours for one rotation. For an object in the distant, cold Kuiper Belt, a region typically associated with slow, ponderous movements over vast timescales, this is like a leisurely waltz suddenly turning into a frantic pirouette. This rapid spin is not just a curious fact, it's a profound clue pointing to forces and events in Quaoar's past that have violently shaped its present. Such a fast rotation has immediate and dramatic consequences for the dwarf planet's shape. In the microgravity environment of small worlds, centrifugal force becomes a powerful sculptor. Imagine a spinning ball of clay. As it rotates faster, it wants to fling material outward from its equator, causing it to bulge and flatten. For Quaoar, this means it is almost certainly not a sphere. Instead, it is very likely an oblate spheroid, a shape much like a squashed ball, significantly wider at its equator than it is from pole to pole. This distortion isn't just superficial, it fundamentally alters the landscape. If you were to stand on Quaoar's equator, you would weigh measurably less than if you stood at one of its poles, because the planet's spin is actively working against its own gravity, trying to throw you off into space. This uneven gravitational field could create a world of extreme geography, with equatorial mountain ranges that are, in a relative sense, easier to climb, and polar regions where everything feels heavier and more compacted. But the most compelling question raised by this rapid spin is its origin. How did Quaoar get wound up so tightly? The most widely accepted explanation points to a violent, cataclysmic event deep in its history, a colossal impact. Picture the early solar system, a chaotic shooting gallery of nascent planets and wandering planetesimals. In this primordial chaos, a young Quaoar, perhaps more spherical and slowly spinning, could have been struck a glancing blow by another large Kuiper Belt object. This wouldn't have been a direct, head-on collision that shatters the world, but more like a cosmic side-swipe, imparting a tremendous amount of angular momentum, setting it spinning like a top. This single event could have been the defining moment for the dwarf planet, setting in motion a chain of consequences that echo billions of years later. This impact hypothesis offers an elegant solution to more than just the spin. It could also explain the very existence of Quaoar's moon, Weywat. The same colossal collision that set Quaoar spinning so rapidly could have blasted an enormous quantity of debris into orbit around it. Over time, just as scientists believe our own moon formed from debris after a giant impact with Earth, this encircling material would have coalesced under gravity to form Weywat. This creates a beautifully linked narrative, a single ancient catastrophe that simultaneously gave Quaoar its fast rotation and its solitary companion. Yet this story, while compelling, is not without its own complications. The precise mechanics of such an impact, the angle and size required to create the specific spin rate we see today while also leaving enough material in a stable orbit to form a moon, is a complex puzzle in itself. The rapid rotation of Quaoar is therefore more than a simple fact. It is a ghostly echo of a violent birth, a permanent record of a moment of cosmic violence that forever set this small world apart from its slower, more sedate neighbors in the frozen darkness. Just when we think we're starting to piece together Quaoar's story from its spin and its ring, we stumble upon a fourth mystery that seems to contradict the evidence right before our eyes: its profound and puzzling silence. Given its composition and distance from the Sun, we would fully expect Quaoar to possess at least a tenuous, seasonal atmosphere. Yet, when astronomers listen closely, they hear nothing but the vacuum of space. This absence of air is a glaring anomaly for a world that should, by all rights, be breathing. The logic for expecting an atmosphere is straightforward. Quaoar's surface is known to be rich in volatile ices, particularly methane and nitrogen. These are the same materials that give larger Kuiper Belt objects like Pluto their thin, hazy skies. As these distant worlds trace their elongated orbits, they experience seasons. When they swing slightly closer to the Sun, surface temperatures rise enough for these frozen ices to transform directly from a solid into a gas, a process called sublimation. This released gas creates a temporary atmosphere. When the world moves back into the deep freeze, the atmosphere condenses and snows back down onto the surface. It's a cosmic cycle of exhalation and inhalation that we see on several Kuiper Belt worlds. Quaoar, with its mix of ices, should be participating in this dance. But the data from stellar occultations is unequivocal. There is no detectable dip in starlight signaling the presence of a gaseous envelope around the dwarf planet. The light winks out sharply as if Quaoar is a stark, bare rock against the stars. So, what is stopping this cycle? The most immediate culprit is Quaoar's modest size and consequently its weak gravity. Think of gravity as a planet's ability to hold onto its coat. A giant like Jupiter has a powerful gravitational grip, easily retaining a thick atmosphere. Even Pluto, though small, has just enough gravitational pull to keep a hold of its nitrogen and methane gases for a portion of its long year. Quaoar, however, is smaller and less massive than Pluto. Its gravity may simply be too feeble to prevent the gases, once sublimated, from escaping entirely into the void. The molecules, energized by what little sunlight reaches them, achieve escape velocity and drift off into space forever. It's like trying to hold onto helium balloons with your bare hands. No matter how hard you try, they inevitably slip away. But gravity alone might not tell the whole story. The nature of the surface ice itself could be a critical factor. What if the volatile ices on Quaoar are not exposed in a way that allows for easy sublimation? Imagine a layer of dark, inert Tholen material complex organic gunk created when sunlight irradiates simple ices acting like a blanket, covering and insulating the more volatile ices beneath. The Sun's energy would struggle to reach the nitrogen and methane, preventing them from turning into gas in the first place. Alternatively, the surface structure could be unusually porous like a cosmic sponge. When the Sun warms it, any gases that do form might get trapped within a labyrinth of microscopic pores and tunnels beneath the surface, never achieving enough pressure to lift off as a true atmosphere. They would remain locked in a subterranean haze, invisible to our telescopes. A third, more dynamic possibility involves Quaoar's rapid rotation. That same dizzying spin that shapes its body could also be actively whipping away any tentative atmosphere that tries to form. The centrifugal force at the equator, which makes the world bulge, also provides a constant push against gases trying to settle there. This could create a situation where any atmosphere is stripped away as fast as it forms, or is funneled strangely towards the poles, creating an atmosphere so patchy and thin that our current instruments cannot detect it. The puzzling lack of an atmosphere, therefore, is not a simple case of a world being too small. It is likely a complex interplay of all these factors: a weak gravitational grip, a surface that may be sealed or porous, and a rapid spin that actively disrupts gaseous envelopes. This silence speaks volumes, telling us that the conditions on these distant icy worlds are far more nuanced and varied than we ever presumed. As if the silent void where an atmosphere should be wasn't puzzling enough, our fifth mystery draws our gaze directly to Quaoar's surface, where stark contrasts of light and dark hint at a world that is far from dead. In the perpetual twilight of the Kuiper Belt, most objects are incredibly dark, their surfaces aged and darkened over billions of years by the relentless bombardment of cosmic radiation, a process that creates a thick, reddish gunk known as tholins. Quaoar generally fits this description, appearing as a dim, dark speck. However, detailed observations have revealed something extraordinary, unexpected patches of startling brightness. These albedo variations, these mysterious bright spots scattered across its landscape, are like fresh wounds on an ancient face, suggesting that geological activity, or something even more surprising, may be recently sculpting this distant world. The existence of these bright patches is a profound clue. On an airless, frozen body so far from the sun, any surface feature should be ancient. The constant rain of micrometeorites and cosmic rays acts like a cosmic sandblaster, steadily darkening everything uniformly. For a patch to remain bright, it must be young, geologically speaking. It implies a process that is either continuously renewing the surface or an event that happened recently enough that the darkening agents haven't had time to do their work. So, what could be causing these brilliant anomalies on such a dark canvas? One of the most thrilling possibilities is cryovolcanism, ice volcanoes. Instead of spewing molten rock, a cryovolcano on a world like Quaoar would erupt with a slush of water, ammonia, methane, or other volatile ices. Imagine a geyser of freezing cold mud bursting through the crust, spreading a fresh, gleaming layer of ice across the dark terrain. This process would effectively resurface the area, creating a bright, new landscape that hasn't yet been darkened by space weather. For cryovolcanism to occur, Quaoar would need an internal heat source to keep its subsurface water in a liquid or slushy state. This is a major revelation, as we typically think of small Kuiper Belt objects as frozen solid all the way through. The energy could come from the decay of radioactive elements in its core, or perhaps from gravitational heating generated by the tidal forces of its moon, Quaoar, flexing Quaoar's interior as it orbits. The presence of bright patches could therefore be indirect evidence that Quaoar is not the inert fossil we assumed, but a world with a complex, warm interior still capable of driving change on its surface. Another compelling explanation points to recent impacts. A collision with a smaller Kuiper Belt object could have blasted away the dark, old surface layer, excavating pristine, brightly reflective ice from beneath the topsoil. We see this effect on other icy bodies, like Jupiter's moon Europa, where impact craters expose bright, clean water ice against a darker background. On Quaoar, the impacting body wouldn't need to be large. Even a relatively small impactor could carve out a bright crater, and in the feeble gravity, the ejected material could be distributed over a wide area, creating a bright splash pattern. This theory is attractive because it doesn't require any ongoing internal activity. It simply points to the dynamic nature of the Kuiper Belt itself, a region where such collisions, while rare, still occasionally occur. A third, and perhaps most exotic, possibility involves seasonal frosts. Even at Quaoar's immense distance, there are slight variations in temperature as it moves along its orbit. While it may not be enough to sustain a full atmosphere, It could be sufficient to cause the sublimation and redeposition of highly volatile ices like nitrogen or methane. Imagine that on the colder side of its long year, temperatures dip just enough for a whisper-thin layer of brilliant white nitrogen frost to condense directly onto the surface, brightening certain areas. Then, as that area turns toward what passes for sunlight, the frost sublimates away only to be deposited elsewhere. This would create a slowly shifting pattern of bright and dark patches, a seasonal cycle on a timescale of hundreds of Earth years. The bright spots we see today might just be the temporary winter coating on particular geological features like crater rims or polar highlands, which are naturally colder. Each of these hypotheses paints a different picture of Quaoar. The cryovolcanic idea suggests a world with a hidden, warm heart. The impact theory portrays it as a passive canvas, still being marked by the occasional violence of its environment. The seasonal frost model implies a world breathing, however faintly, with the rhythms of its orbit. The true answer may well be a combination of all three. Unraveling the origin of these bright patches is not just about understanding Quaoar's appearance. It is about probing its very soul, determining whether it is a static relic or a dynamic, evolving world, quietly active in the deep freeze. Moving from the surface clues to the very heart of this distant world, we encounter our sixth mystery, one that weighs heavily on the minds of planetary scientists: Quaoar's unexpectedly high density. By carefully measuring its size and the orbital dance of its moon, Quaoar, astronomers have been able to calculate the dwarf planet's mass. When they combined that mass with its volume, they arrived at a density that was a genuine surprise. Quaoar is far denser than anyone anticipated for an object in the Kuiper Belt. This is not some fluffy snowball. It seems to be a world with a significant amount of rock packed into its core. This single measurement forces a radical rethinking of what Quaoar actually is and where it came from, suggesting a history far more complex than that of a simple icy remnant. To understand why this is so startling, we need to consider the typical residents of the Kuiper Belt. Most Kuiper Belt objects, especially the smaller ones, are thought to be relatively porous mixtures of ice and rock, often compared to dirty snowballs or loose piles of rubble. Their densities are generally quite low. Pluto, the king of the Kuiper Belt, has a density that indicates a more differentiated structure, a rocky core surrounded by a mantle of water ice, but it is also a much larger world whose internal heat allowed it to separate into distinct layers. For a mid-sized object like Quaoar to possess a density that points to a large, substantial rocky core is highly unusual. It implies that Quaoar is not a primitive, unprocessed lump of primordial material. Instead, it has undergone a significant degree of differentiation, a process where the heavier elements, like rock and metal, sink to the center while the lighter ices rise to form a mantle. This is the kind of geological sorting we associate with much larger, warmer planetary bodies, not with a distant, frozen world that should have cooled off rapidly after its formation. This dense, rocky core opens up a fascinating line of inquiry about Quaoar's formation. One compelling theory is that Quaoar is not a native of its current neighborhood. It may be an immigrant, a planetary building block that formed much closer to the Sun, in the region now occupied by the giant planets. During the solar system's violent youth, the gravitational shoving matches between Jupiter, Saturn, Uranus, and Neptune would have sent countless such objects flying outward, scattering them into the newly forming Kuiper Belt. If Quaoar was born in a warmer, denser part of the protoplanetary disk where rocky material was more abundant, it would have naturally started with a higher rock-to-ice ratio. Its high density today would simply be a fossil relic of its original birthplace. In this scenario, Quaoar is less of a typical Kuiper Belt object and more of a stranded planetesimal, a relic from the inner solar system that was unceremoniously tossed into the deep freeze. Alternatively, Quaoar could be the product of a truly cataclysmic event. Perhaps it is the remnant core of a much larger object that suffered a colossal impact early in its history, an impact so violent that it blasted away most of its original, lighter icy mantle. What we see today would be the stripped-down, dense heart of that former world. This would be analogous to the hypothesized origin of the asteroid Psyche, thought to be the exposed metallic core of a protoplanet. While Quaoar is not metallic, the principle is similar, a traumatic collision revealing a previously hidden interior. This theory could also elegantly tie into its rapid rotation and the formation of its moon, Quaoar, painting a picture of a single, defining moment of cosmic violence that shaped nearly every aspect of the world we see today. The presence of a large rocky core also has profound implications for Quaoar's potential for internal activity. Rock contains radioactive elements like potassium, thorium, and uranium, which decay over time and release heat. A substantial rocky core acts like a built-in nuclear reactor, providing a long-lasting source of internal warmth. This heat could be sufficient to maintain a subsurface ocean of liquid water deep beneath the icy crust, or at the very least to create a warm, slushy mantle. This directly connects back to the mystery of the bright surface patches. That internal heat could be the engine driving cryovolcanic activity, pushing fresh, clean water ice to the surface and renewing the landscape. The high density, therefore, is not just a static number. It's a clue that Quaoar may be a geologically alive world, its cold exterior hiding a surprisingly warm heart that continues to shape its destiny billions of years after its formation. This surprising density, pointing to a rocky core rich in radioactive elements, leads us directly to the seventh and perhaps most transformative mystery of Quaoar, the enigma of its internal heat. In the unimaginable cold of the Kuiper Belt, where temperatures hover just a few tens of degrees above absolute zero, the very idea of a warm world seems like a contradiction. Yet the clues we have, the bright, young surfaces, the possibility of cryovolcanism, all whisper the same tantalizing question. Could Quaoar be generating its own warmth, a flickering fire in the cosmic deep freeze that powers geological activity? Understanding the potential sources of this heat opens a window into the hidden life of this dwarf planet. The most straightforward explanation lies deep within its core, in the slow, steady heartbeat of radioactive decay. Quaoar's rocky interior is likely laced with elements like uranium, thorium, and potassium. These unstable atoms naturally break down over immense timescales, and with each decay, they release a tiny amount of energy in the form of heat. On a small world, this process might not amount to much, but over billions of years, even a modest concentration of these radioactive elements can provide a significant and persistent warmth. It's a built-in nuclear furnace, a source of energy that doesn't depend on the distant sun. This radiogenic heat could be enough to maintain a layer of slushy, warm ice between the rocky core and the frozen outer crust, or perhaps even a global subsurface ocean, much like the ones suspected on moons such as Europa or Enceladus. If this is the case, then Quaoar is not a dead fossil, but a thermally active world, its interior slowly churning over eons. But radioactivity might not be the only actor in this play. Another potent source of internal energy could come from gravitational friction, a phenomenon known as tidal heating. We see this effect dramatically on Jupiter's moon Io, which is relentlessly squeezed and stretched by the gravitational tug of war between Jupiter and its neighboring moons, making it the most volcanically active body in the solar system. While Quaoar's situation is far less extreme, the gravitational pull of its moon, Quaoar, could still be exerting a subtle influence. As Quaoar orbits, its gravity tugs on Quaoar, flexing the dwarf planet's interior. This constant flexing generates friction, and friction produces heat. The efficiency of this process depends heavily on the details of Quaoar's orbit. If the orbit is even slightly eccentric, not a perfect circle but a faint oval, the strength of the tidal pull would vary throughout each orbit, creating a more effective kneading action. This tidal heating could provide a crucial supplemental energy source, working in concert with radioactive decay to keep Quaoar's interior warm and dynamic. We must also consider the possibility that we are witnessing the fading embers of heat left over from the world's very formation. When Quaoar first coalesced from countless smaller planetesimals in the early solar system, each collision released a tremendous amount of energy. This process, known as accretion heating, would have essentially baked the newborn world from the inside out. For a large planet, this primordial heat can take billions of years to dissipate. Earth itself still retains some of this formation heat in its core. For a smaller object like Quaoar, conventional wisdom suggests it should have radiated this energy away and frozen solid long ago. However, if Quaoar formed very quickly, or if it was initially much larger, it could have started with a much larger reservoir of heat. Its thick, insulating icy crust might then act like a thermos, dramatically slowing the cooling process and trapping that ancient warmth for far longer than our models predict. In this scenario, the activity we might be seeing today is the last gasp of a warmth that has been fading since the dawn of the solar system. The true picture is likely a combination of all these factors. Radiogenic decay provides the steady baseline warmth, a constant hum of energy. Tidal heating from Quaoar could add a rhythmic pulse, varying in intensity over time. And the vestiges of accretion heat may still contribute a final few degrees to the total budget. Together, these sources could push Quaoar's internal temperature just high enough to allow for the remarkable geological activity hinted at by its bright surface patches. This transforms our perception of Quaoar from a simple, inert ice ball into a complex thermodynamic system. It suggests that even in the most remote and frigid reaches of our solar system, worlds can harbor their own sources of vitality, challenging our definitions of what it means to be a geologically alive planet and expanding the potential habitats for life in the universe. The mysteries locked within Quaoar extend far beyond its own surface, reaching out into the space around it and focusing our attention on its solitary known companion, the moon Quaoar. Named after the sky god of the Tongva people, the same mythology that gave us Quaoar, Quaoar is more than just a silent partner. It is a key witness to Quaoar's history and a crucial piece of the gravitational puzzle. From its distant orbit, estimated to be roughly 14,000 kilometers from Quaoar, Quaoar takes about 12.5 Earth days to complete a single circuit. It's a small world in its own right, likely only about 80 kilometers across, but its motion is a precise instrument for astronomers. By carefully tracking the orbit of Quaoar, scientists were able to perform a cosmic weigh-in, calculating Quaoar's mass with remarkable accuracy. It was this very measurement that revealed the dwarf planet's unexpectedly high density, telling us that Quaoar possesses a significant rocky core. In this way, Quaoar acts as a gravitational probe, its path dictated by the mass hidden beneath Quaoar's icy crust, revealing secrets about the interior that we could never learn by looking at the surface alone. Yet the story of Quaoar's satellites may not be a simple solo act. This brings us to the ninth mystery, the compelling possibility that Quaoar is not alone. Astronomers have scrutinized the data and found subtle hints that point to the existence of a second, much smaller moon. The evidence is indirect but persuasive, lurking in the fine details of gravitational dynamics. When scientists model Quaoar's orbit around Quaoar, they sometimes detect tiny, unexplained deviations, minuscule wobbles or accelerations that their calculations can't quite account for if Quaoar is the only significant gravitational body in the system. These perturbations are like faint ripples in a pond, suggesting that an unseen object, a hidden moonlet, is gently tugging on Quaoar, ever so slightly altering its path through space. This gravitational whisper is a classic technique in astronomy. It's how Neptune was discovered by its effect on Uranus's orbit, and how we often find exoplanets around distant stars. Another line of evidence comes from the same stellar occultation events that revealed Quaoar's impossible ring. As Quaoar passed in front of a star, astronomers meticulously recorded the precise moments the starlight vanished and reappeared. Amidst the data showing the main body of Quaoar and its ring, there may have been additional, incredibly brief dips in brightness, so short they lasted only a fraction of a second. These fleeting flickers could be the signature of a small, unseen moon passing in front of the star, blocking its light for a mere instant. Spotting such an event is akin to finding a needle in a cosmic haystack. It requires impeccable timing and a bit of luck. The hypothetical second moon would likely be very small, perhaps only 10 to 20 kilometers in diameter, and incredibly dark, making it virtually invisible to our telescopes against the blackness of space. Its orbit would probably be closer to Quaoar than Quaoar's, or perhaps much farther out, but in either case, its gravitational influence would be a subtle but detectable force on the system. Confirming the existence of this moonlet is one of the foremost challenges in Quaoar science. The primary obstacle is its likely minuscule size and dark surface. In the faint light of the distant sun, detecting such a small object is at the very limit of what even the Hubble Space Telescope or the James Webb Space Telescope can achieve. It would appear as a point of light indistinguishable from background stars, requiring multiple observations over time to confirm it is actually moving with Quaoar. The best hope for confirmation lies in future, highly sensitive occultation campaigns, or perhaps by using the most advanced telescopes to conduct a painstaking pixel-by-pixel search of Quaoar's immediate vicinity. The discovery of a second moon would radically reshape our understanding of the Quaoar system. It would provide another clue to its violent past, perhaps being another remnant of the same ancient collision that formed Quaoar. Furthermore, its gravity could play a crucial role in shepherding the particles of the mysterious ring, solving one puzzle while undoubtedly creating several new ones about the complex orbital dance happening in the deep freeze. While Quaoar's internal mysteries and its celestial companions captivate our imagination, to truly understand this world we must step back and observe its grand celestial waltz around the sun. This brings us to the 10th great mystery, Quaoar's surprisingly orderly and placid orbit. In the chaotic and often unruly neighborhood of the Kuiper Belt, Quaoar is an island of calm, its path around the sun marked by a peculiar circularity and a modest tilt that set it apart from its wilder neighbors. This tranquility is not a mere curiosity. It is a potential timestamp, a clue that Quaoar may be a pristine relic from the very dawn of our planetary system. Most large Kuiper Belt objects like Pluto, Eris, and Haumea follow orbits that are distinctly elliptical or oval-shaped. Their journeys around the sun are a story of extremes. They swing dramatically close to the star before hurtling back out into the deepest freeze. Pluto, for instance, even dips inside the orbit of Neptune for a portion of its long year. These highly eccentric orbits are the hallmark of a violent history. They are the cosmic scars left by gravitational encounters with the giant planets, particularly Neptune, during the solar system's chaotic infancy. A close pass with a massive world can act like a gravitational slingshot, stretching a previously circular orbit into an elongated one, flinging an object into a new and more extreme path. Many Kuiper Belt objects also have high orbital inclinations, meaning their orbits are tilted significantly relative to the flat plane where the planets orbit. This, too, is a sign of a dramatic past, a gravitational shove that knocked them out of the primordial disk. Quaoar, in stark contrast, follows a path of remarkable restraint. Its orbit is far more circular than those of its famous cousins. It maintains a relatively constant distance from the Sun, never venturing too close nor straying excessively far. Furthermore, its orbital inclination is quite mild, keeping it contentedly within the general plane of the solar system. This placid trajectory suggests a profoundly different life story. It implies that Quaoar has been a cosmic hermit, keeping to itself for billions of years. it has likely avoided the violent gravitational encounters that reshaped the orbits of so many other Kuiper Belt objects. While worlds like Pluto were being tossed around by Neptune's gravity, Quaoar seems to have remained in a stable, quiet corner of the solar system, untouched by the chaos. This peaceful existence points to a thrilling possibility. Quaoar could be a primordial object, a genuine fossil from the era of planet formation. It may have formed precisely where we find it today, or very close by, and has remained in that stable orbit undisturbed for 4.5 billion years. If this is true, then Quaoar is not a scattered refugee from the inner solar system, but a local, one of the original building blocks of the planetary system that never got incorporated into a larger planet. Its composition and structure would therefore represent a pristine sample of the material that existed in this specific region of the protoplanetary disk. Studying Quaoar would be like opening a time capsule, giving us an unprecedented look at the conditions and ingredients present when the planets were first assembling. However, this narrative of a quiet life introduces a fascinating tension with the other mysteries we've already explored. How do we reconcile this placid orbital history with the evidence of a violent past written across Quaoar itself? Its rapid spin and the potential formation of its moon from a giant impact suggest a moment of tremendous cosmic violence. This creates a compelling paradox, a world with a calm exterior but a turbulent inner history. One resolution could be that the colossal impact that shaped Quaoar occurred very, very early, perhaps even before the orbits of the giant planets were fully settled. The impact itself could have been a local event, a collision with another primordial body within the Kuiper Belt that did not require the gravitational intervention of a giant planet. After this defining cataclysm, Quaoar's orbit may have simply remained stable, its gravitational interactions with Neptune and the other giants being minimal or non-existent. Its orderly orbit, therefore, doesn't necessarily rule out a violent birth. It just suggests that after that birth, it was left alone to slowly cool and evolve in isolation. This combination of a dramatic formation and a serene subsequent existence makes Quaoar a uniquely complex world, a testament to the fact that the early solar system was a place of both immense chaos and surprising pockets of order. Yet another layer of Quaoar's mystery is written in the very light it reflects back to us, a cryptic message deciphered through the science of spectroscopy. When astronomers analyze the sunlight that bounces off Quaoar's surface, they are essentially taking its chemical fingerprint. Each molecule and compound absorbs and reflects specific wavelengths of light, creating a unique spectral signature. What they found was a complex and puzzling mix, a recipe that doesn't quite match any other known world in the Kuiper Belt. The spectrum confirms the presence of water ice, which is expected for a frozen body, but it is water ice that seems strangely crystalline, not the amorphous, glass-like ice that should dominate in such a cold environment. Intermingled with this ice are dark, ruddy materials, amorphous carbon, which is essentially soot, and most intriguingly, a significant amount of tholins. Tholins are not a single compound but a class of complex organic polymers. They are created when simple ices like methane or nitrogen are bombarded by ultraviolet radiation from the sun or cosmic rays. This process, a slow cosmic chemistry experiment played out over billions of years, breaks apart the simple molecules and reassembles them into large, complex, tar-like substances that are typically reddish-brown in color. Tholins are thought to be widespread in the outer solar system, giving places like Pluto and Titan their distinctive reddish hues. Their presence on Quaoar indicates an ancient surface that has been thoroughly processed by radiation. However, the puzzle lies in the combination. The coexistence of these dark, ancient tholins with relatively fresh, crystalline water ice is a paradox that challenges our models of how surfaces evolve in the Kuiper Belt. If Quaoar's surface were as old as the solar system itself, the constant irradiation should have long ago destroyed the orderly crystalline structure of its water ice, turning it into amorphous ice. The fact that the spectral signature still shows signs of crystalline structure suggests a surface renewal process. Something is either bringing fresh, clean water ice from the interior to the surface, or it is somehow reheating the existing surface ice enough to recrystallize it. This directly supports the idea of cryovolcanism or other geological activity. Imagine a slush of relatively warm water ice erupting from beneath the crust, spreading a new layer that quickly freezes into a crystalline form, only to be slowly darkened over time by the formation of new tholins. The spectrum we see today would then be a snapshot of this ongoing battle between renewal and decay. The amount and type of tholins present also tell a story. The specific spectral features suggest that the tholins on Quaoar are particularly complex, possibly indicating a unique mix of the original ices that were available for irradiation. Perhaps Quaoar started with a different blend of methane, nitrogen, and other hydrocarbons than its Kuiper Belt neighbors, leading to a distinct flavor of tholin. Alternatively, the varying temperatures across Quaoar's surface, influenced by its rapid rotation and possible oblateness, could create micro-environments where tholin formation is more or less efficient. The patches of bright ice we see could be areas where this organic gunk has been recently covered or where the formation process is inhibited. This unique spectral fingerprint, therefore, does more than just list ingredients. It provides a detailed, albeit confusing, history book of Quaoar's surface, recording billions of years of radiation exposure punctuated by episodes of geological rejuvenation. It is the signature of a world that is neither entirely dead nor fully understood, a dynamic interface between a hidden interior and the harsh environment of space. The spectral evidence of crystalline ice and bright surface patches leads us to a truly transformative idea: that Quaoar is not a static fossil but a world capable of remaking its own face. This is our 12th mystery, the compelling possibility of recent surface renewal. In the deep freeze of the Kuiper Belt, where most surfaces are ancient archives cratered by impacts over 4 billion years, the existence of any youthful terrain is a sign of profound internal activity. It suggests that forces deep within Quaoar are still at work, pushing, heating, and erupting to wipe the slate clean and create new landscapes against all odds. The most dramatic mechanism for this renewal is cryovolcanism. Picture not a volcano of fire and brimstone, but one of ice and cold mud. On Quaoar, a cryovolcano would tap into a subsurface reservoir of liquid or slushy water, likely mixed with antifreeze agents like ammonia or methanol. This frigid slurry, kept liquid by the internal heat from radioactive decay or tidal forces, would be less dense than the solid icy crust above it. Under pressure, it would find a weak spot, a fracture or a fault, and force its way to the surface. The eruption would not be explosive like Mount St. Helens, but more like a slow, viscous ooze, spreading a vast, smooth layer of fresh, bright ice across the dark, old terrain. This process would effectively resurface entire regions, erasing the accumulated scars of countless micrometeorite impacts and covering the dark, radiation-baked tholins with a gleaming new coat of paint. The bright patches we observe could be the frozen flows from such eruptions, their crystalline structure a testament to their recent arrival from the relative warmth of the interior. But volcanism isn't the only way to renew a surface. Another possibility is large-scale tectonic activity. We tend to think of tectonics as something that happens on rocky planets like Earth, where plates of crust shift and grind against each other. On an icy world, the processes are different but can be just as effective. Quaoar's rapid rotation and its subsequent cooling and contraction over billions of years could create immense stresses in its outer shell. This stress might cause the icy crust to crack, with large sections shifting relative to one another. These tectonic shifts could push older, cratered terrain downward, subducting it beneath newer plates of ice, much like ocean crust is consumed beneath continents on Earth. Alternatively, the crust could stretch and thin, allowing warmer material from below to well up and refreeze, creating vast, smooth plains that have been repaved from below. This kind of activity would not necessarily involve eruptions, but rather a slow, colossal shuffling of the surface itself, creating young-looking plains that lack the heavy cratering of their surroundings. A third, more subtle form of renewal could come from the slow redistribution of surface ices. Even at Quaoar's immense distance, there is a tiny amount of solar energy. Over millions of years, this minuscule input could be enough to cause the sublimation and recondensation of the most volatile ices, like nitrogen or methane. Imagine a process akin to water vapor on Earth moving from oceans to clouds to precipitation, but happening at a geological pace. The dark, tholin-rich material on Quaoar's surface absorbs slightly more sunlight than bright ice, causing it to warm up just a fraction of a degree more. This could be enough to make any trace amounts of volatile ice on these dark patches sublimate. The gas would then drift across the surface until it encounters a colder area, such as a bright, high-albedo region or a permanently shadowed crater floor, where it would condense back into a frost. Over eons, this could lead to a natural segregation, with dark areas getting darker and brighter areas getting brighter, creating a constantly evolving, if incredibly slow, pattern of renewal through seasonal cycles that last for centuries. Each of these mechanisms paints a different picture of Quaoar's geological personality. Cryovolcanism suggests a world with a warm, potentially ocean-bearing interior that occasionally bursts forth. Tectonics implies a world with a dynamic, brittle crust that is still cracking and shifting under internal and rotational stresses. The redistribution of volatiles portrays a world that breathes, however faintly, with the rhythm of its orbit. What makes this mystery so profound is that the evidence points toward activity that is not just ancient, but potentially ongoing or at least geologically recent. If parts of Quaoar's surface are only a few 100 million years old, a blink of an eye in solar system terms, then it forces us to categorize this distant dwarf planet not as a dead relic, but as a living world, one of a rare group of active bodies that continue to shape their own destinies in the silent vastness of space. As we piece together the clues from Quaoar's surface and orbit, our investigation takes a fascinating turn outward, connecting this solitary world to one of the most dramatic events in the outer solar system. This brings us to the 13th mystery, the compelling hypothesis that Quaoar may not be an isolated world at all, but rather a surviving fragment from a cosmic catastrophe of unimaginable scale, the collision that created the strange Haumea family of Kuiper Belt objects. To understand this possibility, we need to first meet Haumea itself, a world that is arguably the solar system's most conspicuous oddball. Haumea is a rapidly spinning, football-shaped dwarf planet, completing a rotation in less than 4 hours, a speed that has stretched it into a distinct ellipsoid. But its true claim to fame is its extended family. Haumea is surrounded by a swarm of smaller Kuiper Belt objects that share nearly identical orbits and, most tellingly, the same unique, brilliantly reflective surface of pure water ice. The leading theory is that billions of years ago, a giant impact shattered a larger, icy protoplanet. The largest remaining piece became Haumea, sent spinning wildly from the blow, while the debris from the collision was scattered into space, eventually settling into the cluster of objects we see today. These family members are essentially siblings, all born from the same violent event. So, where does Quaoar fit into this family portrait? The potential link lies in a few tantalizing pieces of evidence. First, there is the spectral signature of water ice. Both Quaoar and the Haumea family members show evidence of crystalline water ice on their surfaces. While water ice is common in the Kuiper Belt, the specific crystalline structure is more noteworthy because it suggests a surface that is relatively young or has been recently processed. In the case of the Haumea family, the ice is exceptionally bright and pure, believed to be the fresh interior material exposed by the colossal impact. If Quaoar is a distant cousin from that same event, the crystalline ice on its surface could be a heritage from its origin, a pristine sample of the interior of that long-lost parent body. The second, and perhaps more compelling, clue involves their orbits. While Quaoar's orbit is more circular and placid than those of the core Haumea family members, there are subtle dynamical similarities that have caught the attention of astronomers. Computer models simulating the giant impact that created the Haumea family show that the debris would not have all been ejected onto identical paths. Some fragments could have been thrown onto slightly different trajectories, their orbits gradually evolving over billions of years due to the subtle gravitational tugs of Neptune. It is conceivable that Quaoar started its life as one of these larger, ejected fragments. Over the eons, its orbit could have been gently nudged by planetary perturbations into the more stable, circular path we observe today, distancing it dynamically from its more tightly clustered siblings while retaining the physical characteristics of its birth. However, this fascinating theory faces significant challenges. The most substantial hurdle is composition. The Haumea family members are famously covered in almost pure water ice, with very little of the dark, reddened tholin material that is so evident on Quaoar's surface. If Quaoar were a fragment from the same icy parent body, why does it appear so much darker and more processed? Proponents of the connection argue that Quaoar's larger size and greater mass could be the key. As a larger object, it would have a stronger gravitational pull, allowing it to attract and hold onto a cloak of darker dust and debris over time through impacts with smaller, carbon-rich objects in the Kuiper Belt. A smaller Haumea family member with its weak gravity might have been unable to hold onto such a dark coating, leaving its bright, icy surface exposed. Alternatively, Quaoar's potential internal activity and cryovolcanism could have brought up darker material from its interior, obscuring its original, bright surface, a process not seen on the smaller, inert fragments of the family. The debate is far from settled, and the question of Quaoar's lineage remains one of the great detective stories of modern astronomy. If the connection is proven, it would fundamentally reshape our understanding of Quaoar's history. It would mean that its rapid spin and possible moon-forming impact are not isolated events, but are directly tied to the most famous fragmentation event in the Kuiper Belt. Quaoar would transform from a solitary enigma into a lost patriarch, a large surviving piece of a vanished world, carrying the secrets of that ancient collision in its core. If the link is disproven, then Quaoar's story becomes even more remarkable, indicating that its own violent history and unique properties are entirely its own, the result of a separate, equally dramatic cataclysm. Either outcome deepens the mystery, revealing a solar system infancy that was far more violent and interconnected than we ever imagined, with Quaoar sitting at the heart of the puzzle. But even as we consider Quaoar's possible family ties, we must turn our attention to a more immediate and measurable mystery, the puzzle of its surface temperature. In the near-absolute zero environment of the Kuiper Belt, the concept of a hotspot is relative, amounting to perhaps just a few degrees of difference. Yet, for astronomers, these tiny thermal variations are like bright signals, revealing the complex character of a world billions of miles away. The 14th mystery of Quaoar is a thermal one. This distant dwarf planet does not present a uniform, icy chill. Instead, it appears to have a patchwork of slightly warmer and colder regions, a temperature anomaly that speaks volumes about what is happening on and below its surface. Measuring such infinitesimal temperature differences from Earth is a feat of extraordinary technological ingenuity. It relies on sensitive instruments that can detect the faint heat signature Quaoar emits in the form of far-infrared and microwave radiation. Telescopes equipped with advanced bolometers, which are essentially ultra-sensitive thermometers, can map the thermal energy coming from different parts of the distant world as it slowly rotates. Because Quaoar is so small in our sky, this isn't a detailed picture like a weather map of Earth. Instead, it's about detecting subtle shifts in the overall thermal output as different regions turn toward us. By carefully analyzing this data over time, scientists can infer that the surface is not a single, uniform temperature, creating a puzzle with several compelling potential solutions. The most straightforward explanation for these thermal variations lies in simple differences in composition and color. Just as a black asphalt parking lot gets much hotter in the sun than a light-colored concrete sidewalk, the dark, reddish-tholin-rich regions on Quaoar are more effective at absorbing the tiny amount of solar energy that reaches them. These dark patches would become slightly warmer than the brilliant, bright patches of freshwater ice, which reflect most of the sunlight away. This creates a natural thermal mosaic where the ancient, dark terrain acts as a more efficient solar heater, while the young, bright ice remains in a deeper chill. The temperature map, in this case, would be a direct reflection of the surface composition we've already detected spectroscopically. However, topography can also play a powerful role. Imagine a deep impact crater on Quaoar, its floor perpetually in shadow. This area would be a permanent cold trap, likely one of the coldest places on the entire world, where any volatile gases would freeze solid. Conversely, a tall mountain peak or the crest of a large crater rim would be more exposed to the feeble sunlight, potentially making it a relative high point on the thermal map. The way sunlight strikes slopes facing the sun versus those facing away could create significant local temperature gradients, all driven by the angle of incidence on a world with no atmosphere to redistribute the heat. The rapid rotation of Quaoar adds another layer of complexity, as these hot and cold spots would be constantly shifting in and out of view from our perspective, creating a dynamic, if subtle, thermal pulse. The most thrilling possibility, though, is that these temperature anomalies are not just skin deep. What if the warmer spots are not merely absorbing more sunlight, but are actually venting heat from the dwarf planet's interior? This would be the smoking gun for ongoing geological activity. A fissure or crack in the icy crust caused by tectonic stresses could act as a conduit for internal warmth to reach the surface. Even a small trickle of heat from a slushy mantle or a subsurface ocean would be enough to create a detectable warm spot against the intensely cold background. This wouldn't be a volcano of flowing lava, but a gentle, persistent seepage of geothermal energy, subtly raising the local temperature. If such a vent were located near one of the bright patches, it would powerfully support the cryovolcanic hypothesis, suggesting that the fresh ice we see was not only brought up from below but may still be warmed by the forces that raised it. Unraveling the temperature anomaly puzzle is therefore critical. It helps distinguish between a world that is passively painted by the sun and one that is actively generating its own warmth, a fundamental distinction that separates a living world from a dead one. Now we turn our attention to a mystery that unfolds in the realm of pure light and shadow, one that astronomers detect not by looking at images of Quaoar, but by patiently charting its faint glimmer against the starry backdrop. This is the 15th mystery, the unexplained variations in Quaoar's light curve. Since it's too distant and small for our telescopes to resolve its shape directly, scientists rely on a clever technique. They measure its brightness with immense precision over time, watching as it rotates. For a perfectly spherical world, this light curve would be almost flat. The amount of reflected sunlight would remain constant. But Quaoar's brightness does not stay constant. It pulses, rising and falling in a distinct, repeating pattern that reveals this world is anything but round. These fluctuations are the key to mapping its hidden topography, telling a story of a profoundly irregular and lumpy world. The most immediate conclusion from this wobbly light curve is that Quaoar possesses a highly irregular shape. As different faces of the dwarf planet turn toward Earth, the amount of surface area reflecting sunlight back to us changes. When a broader, more face-on area is presented, the object appears brighter. When we are looking at it end-on, perhaps toward a more narrow pole, it dims. The specifics of the light curve's pattern, the speed of the brightness changes, and their amplitude allow astronomers to create detailed models of the possible shapes that could produce such a signal. The models strongly suggest that Quaoar is not a simple oblate spheroid, gently squashed by its rotation, but something far more jagged and asymmetrical. This irregularity is a direct window into the dwarf planet's internal strength, or surprising lack thereof. One compelling explanation for such a lumpy form is that Quaoar might be what is known as a rubble pile asteroid, but on a gigantic scale. This theory proposes that Quaoar is not a solid, monolithic chunk of rock and ice. Instead, it could be a loose collection of countless smaller boulders, rocks, and ice chunks, all held together by their mutual gravity like a cosmic gravel pile. In this scenario, the dwarf planet's overall shape is not determined by the structural strength of its material, but by the balance of gravitational and rotational forces. Its fast spin would naturally cause such a loosely bound aggregate to bulge at its equator and become misshapen, easily explaining the asymmetries seen in the light curve. A rubble pile structure would also have profound implications for its history, suggesting it formed from the gentle accumulation of smaller bodies rather than from a cataclysmic impact, and that its interior could be porous and fractured. However, an equally dramatic possibility is that we are witnessing the scar of a monumental collision. The irregularity in the light curve could be caused by a single, colossal feature, a giant impact basin, so vast it dramatically alters the world's profile. Imagine a crater hundreds of kilometers across, gouged out of Quaoar's surface by an ancient impact. As this gigantic dent rotates into view, it would present a significantly different surface area and angle to the Sun, causing a pronounced dip in the overall brightness. The dwarf planet would essentially have a massive flat spot or a deep concavity that breaks the smooth curve of its shape. This would align beautifully with the impact hypothesis for its rapid rotation and the formation of its moon, Quaoar, painting a picture of a single, defining catastrophic event that left its mark on the world's shape, spin, and satellite system. A third and more subtle hypothesis looks to the skies around Quaoar for an answer. The gravitational pull of a substantial, yet undiscovered, second moon could be literally twisting Quaoar out of shape. We are accustomed to thinking of a planet's gravity shaping its moons, but the opposite is also true, especially if the moon is sizable and in a close orbit. The persistent tidal tug from a hidden companion could create a permanent bulge on Quaoar, a gravitational mountain that is locked in place relative to the moon's position. As Quaoar rotates, this fixed bulge would cause a regular variation in brightness as it presents itself differently to Earth-based observers. This would mean the irregularity isn't a static feature of Quaoar's crust, but a dynamic deformation, a continuous gravitational dance between the dwarf planet and a hidden partner. Each of these possibilities, a rubble pile structure, a giant crater, or tidal deformation, carries dramatically different implications for understanding Quaoar's fundamental nature. The rubble pile model suggests a world that is fragile and loosely assembled. The giant crater theory points to a world that is solid but brutally scarred. The tidal deformation idea implies a world that is still actively being molded by its cosmic companions. The true answer likely lies in a combination of these factors. Perhaps Quaoar has a rubble pile interior that was then sculpted by a giant impact and is now being subtly tweaked by the gravity of its moons. The unexplained light curve variations are therefore a perfect example of how a simple measurement of brightness can open a portal into the deepest secrets of a world's composition, history, and the dynamic forces that continue to shape it across billions of years. Moving from the global puzzle of its shape to the specific chemistry of its surface, we encounter our 16th mystery, the curious case of Quaoar's missing methane. In the frozen menagerie of the Kuiper Belt, methane ice is a common ingredient. Large worlds like Pluto, Eris, and Makemake are all bedecked with significant patches of this frozen hydrocarbon, which gives their surfaces particular spectral signatures and influences their seasonal cycles. Given its size and location, we would naturally expect Quaoar to share in this methane abundance. Yet, when scientists analyze its surface composition, they find a noticeable deficit. The methane is there, but in quantities far lower than the standard models predict, presenting a classic cosmic detective story with three primary suspects: escape, burial, or a dramatic transformation. The first and most straightforward explanation is that Quaoar's methane has simply vanished into the void. This process of atmospheric escape is a constant, slow leak for small worlds with weak gravity. Even at Quaoar's frigid temperatures, the tiny amount of energy from the distant sun can be enough to energize methane molecules on the surface, allowing them to break free from the dwarf planet's gravitational grasp. This is especially true if the methane ever sublimates into a gaseous state. On a larger world like Pluto, gravity is just strong enough to hold onto a temporary atmosphere of nitrogen and methane during the warmer parts of its orbit. But Quaoar's weaker pull may make such retention impossible. Any methane that turns to gas might be immediately lost, a continuous trickle of molecules escaping into the endless night of space over billions of years. In this scenario, Quaoar started with a normal methane supply but has been bleeding it away ever since, leaving behind a surface relatively depleted of this volatile ice. A second possibility is that the methane is not gone but hiding. Quaoar's surface is a complex landscape, likely covered by a layer of dark, complex tholins and other radiation-made gunk. This material could act as a protective blanket, covering vast reservoirs of pristine methane ice that lie buried just beneath the surface. Imagine a layer of cosmic topsoil, several meters thick, shielding the frozen methane from direct sunlight and thus preventing it from sublimating or being directly broken down by radiation. This methane could be a relic from Quaoar's formation, preserved in a deep freeze that has remained intact for eons. Evidence for this comes from the possibility of cryovolcanism or impacts. If an event were to excavate a fresh crater, it might expose this hidden, bright methane ice, which would then slowly darken over time. The apparent depletion on the surface, then, would be an illusion, a matter of what is visible to our telescopes versus what is actually present beneath the dusty veneer. The third, and perhaps most chemically intriguing, suspect is transformation. Methane, a simple molecule of one carbon atom and 4 hydrogen atoms, is a fragile thing when exposed to the harsh environment of space. Bombarded relentlessly by cosmic rays and ultraviolet radiation from the sun, its chemical bonds can be broken. The freed carbon atoms can then link together into long, complex chains, combining with nitrogen and other elements to form those dark, reddish tholins that give Quaoar its characteristic color. This process is essentially a slow, billion-year-long cooking process, turning simple ices into complex organic goo. If this is the primary mechanism, then Quaoar's missing methane isn't missing at all. It has been converted, its spectral signature morphing into something entirely different. The degree of this transformation could be more advanced on Quaoar than on its neighbors, perhaps because its surface is older. It lacks a protective atmosphere, or its unique orbital history has exposed it to a different dosage of radiation. In this light, the dark tholins that coat Quaoar are not just a surface covering. They are the ghost of its former methane, a chemical tombstone marking the demise of the simple ices that once were. Unraveling this conundrum is crucial because it speaks to the fundamental life story of Quaoar and its place in the Kuiper Belt. If the methane has escaped, it tells us about Quaoar's inability to hold onto volatiles, reinforcing its identity as a world with feeble gravity. If the methane is buried, it suggests a geologically layered world with a history of surface deposition, and it implies that future missions could find pristine, ancient ice just below the surface. But if the methane has been transformed, then Quaoar becomes a showcase for the complex chemical evolution that is possible in the outer solar system, a natural laboratory where the raw ingredients of life's building blocks are being synthesized through non-biological processes. The answer likely involves a combination of all three processes, but determining their relative importance will help us understand not just Quaoar, but the ultimate fate of volatile ices on all small, distant worlds. This brings us to a mystery that is fundamental not just to Quaoar, but to our entire classification of small worlds, its position in a critical cosmic size gap. Quaoar is not among the largest dwarf planets, nor is it one of the myriad tiny ice balls that populate the Kuiper Belt. Instead, it occupies a fascinating and crucial middle ground, a planetary purgatory that makes it one of the most important objects we have ever found for understanding the transition from simple cosmic debris to complex, active worlds. Understanding this in-between status is like finding a missing link in the evolutionary chain of planetary bodies. On the smaller end of the scale, we have the vast majority of Kuiper Belt objects. These are the cometary nuclei and small, irregular lumps of ice and rock, typically less than a few hundred kilometers across. For these worlds, size is destiny, and that destiny is stillness. Their small masses mean they have very little gravity to compact their interiors, and they lack sufficient radioactive elements to generate significant internal heat. As a result, they cooled off rapidly after their formation billions of years ago and have remained essentially frozen in time ever since. They are the fossils of the solar system, their surfaces ancient archives of impacts, their shapes often bizarre and irregular because their gravity is too weak to pull them into a sphere. They are simple, inert, and predictable. On the opposite end of the spectrum, we have the dwarf planet royalty like Pluto and Eris. These are the giants of the Kuiper Belt with diameters well over 2,000 kilometers. Their greater mass grants them several transformative powers. First, their stronger gravity forces them into a nearly perfect spherical shape, a hallmark of planetary bodies. More importantly, their size allows them to retain the heat from their formation and from the decay of radioactive elements in their substantial rocky cores. This internal warmth powers a geological heart driving processes like cryovolcanism, tectonic activity, and the slow churning of their icy mantles. Pluto, we now know, has a subsurface ocean, towering mountains of water ice, and vast glaciers of nitrogen. These are not dead rocks, they are dynamic, evolving worlds. Quaoar sits squarely in the no-man's land between these two categories. With a diameter of about 1,100 kilometers, it is too large to be a simple inert lump, yet seemingly too small to possess the kind of robust internal heat that fuels the geology of Pluto. This is what makes it so incredibly valuable. Quaoar is a natural laboratory, testing the very limits of how small a world can be and still be geologically alive. The clues we've already uncovered, its high density suggesting a rocky core, its bright patches hinting at surface renewal, its possible internal heat, all indicate that it may be right on the cusp of this transition. It might represent the minimum size threshold for planetary complexity. This size gap status forces us to ask profound questions. Is there a specific diameter where a cold, dead world suddenly wakes up? Or is it a more gradual process where each additional kilometer of size adds a little more internal pressure, a little more radioactive material, slowly tipping the balance from fossil to active world? Quaoar suggests the latter. It may not have the dramatic nitrogen glaciers of Pluto, but it seems to be capable of more than just sitting in the dark. Its potential for cryovolcanism or tectonics, however modest, shows that geological activity isn't an on-off switch reserved for the largest worlds. It's a dimmer switch, and Quaoar's light, while faint, is unmistakably on. By studying this in-between world, we are essentially calibrating our models for what is possible on small, icy bodies throughout the universe, including the icy moons orbiting planets in our own solar system and around other stars. Quaoar is the key that unlocks the door between two fundamentally different classes of celestial object, proving that even in the deep freeze, size truly does matter. One of the most profound and captivating questions raised by Quaoar's hidden warmth is whether this distant world could be harboring one of the universe's most precious resources, a liquid water ocean. The very idea seems to defy logic, a notion of liquid existing in a realm of perpetual, deep freeze cold. Yet the clues we've gathered, the potential for internal heat from radioactive decay, the evidence of recent surface renewal all point toward a world that is far from inert. The possibility that Quaoar joins an elite group of ocean worlds, like Jupiter's moon Europa or Saturn's Enceladus, transforms it from a simple icy fossil into a potential haven for exotic chemistry and perhaps even the conditions for life. For a subsurface ocean to exist on Quaoar, two critical conditions must be met. The first is a reliable and persistent source of internal heat. The cold of space is relentless, and without an energy source to counter it, any liquid water would have frozen solid billions of years ago. This is where Quaoar's surprisingly high density becomes so important. Its substantial rocky core, likely rich in radioactive elements like potassium, thorium, and uranium, acts as a built-in nuclear furnace. The slow, steady decay of these atoms releases heat, warming the interior from the inside out. This radiogenic heat could be sufficient, especially when combined with any residual warmth from its formation or supplemental tidal heating from its moon, to maintain a layer of liquid water sandwiched between the frozen outer crust and the solid rocky core. The ocean wouldn't need to be globally vast. It could be a regional sea or a layer of slushy, briny water mixed with ice, but its mere existence would be revolutionary. The second crucial ingredient is an antifreeze. Pure water would freeze at the temperatures found at Quaoar's depth, even with an internal heat source. However, if the water is mixed with certain salts and ammonia, its freezing point can be dramatically lowered. Ammonia, in particular, is a powerful antifreeze that is common in the outer solar system. If Quaoar's original building blocks included a significant amount of ammonia hydrate ice, this compound could now be dissolved in a subsurface water reservoir, creating a bitter, cold brine that remains liquid at temperatures far below 0 degrees Celsius. This isn't a warm, tropical ocean. It would be a dark, dense, and profoundly cold abyss, but liquid nonetheless. The presence of such antifreeze agents is considered highly likely for a world that formed in the ammonia-rich environment of the Kuiper Belt. So how could we ever hope to confirm such a hidden ocean? Future missions to the outer solar system would need to employ a suite of sophisticated instruments. One of the most telling signs would be a measurement of Quaoar's libration, a slight wobble in its rotation as it orbits the Sun. A solid world where the crust is firmly locked to the core would have a very predictable, rigid rotation. But if a global ocean separates the icy shell from the rocky interior, that outer shell can rotate somewhat independently, creating a tiny but detectable wobble that sophisticated radar or laser altimetry from a passing spacecraft could measure. Another method would involve a detailed analysis of Quaoar's gravitational field. By precisely tracking the path of a spacecraft flying close to the dwarf planet, scientists could map the subtle lumps and bumps in its gravity. A subsurface ocean would allow the icy crust to flex more easily under the gravitational pull of its moon, Quaoar, creating distortions in the gravity field that betray the presence of a liquid layer below. Perhaps the most dramatic evidence would be the discovery of active plumes, similar to those seen erupting from Enceladus. If Quaoar's subsurface ocean is under pressure and maintains contact with the surface through cracks or fissures, cryovolcanic geysers could be spewing a mixture of water vapor and other compounds into space. A spacecraft equipped with a mass spectrometer flying through such a plume could directly sample the composition of the hidden ocean, analyzing it for salts, organic molecules, and other indicators of habitability. While we have not yet observed such plumes on Quaoar, their potential existence makes this distant world a prime target in the search for life beyond Earth. The discovery of a subsurface ocean on Quaoar would fundamentally reshape our understanding of where life could potentially arise, proving that even in the most remote and seemingly inhospitable corners of our solar system, the essential ingredient of liquid water can persist against all odds. But to truly peer into the chemical soul of Quaoar, we must move beyond reflected sunlight and into the realm of its own faint glow, which brings us to our 19th and perhaps most chemically tantalizing mystery, the strange emission lines detected in its infrared data. When astronomers point powerful infrared telescopes like the James Webb Space Telescope toward Quaoar, they are not just looking for what the world reflects, but for what it emits, the unique thermal fingerprint of its constituent molecules. Every chemical compound, when warmed even slightly, vibrates and radiates energy at specific characteristic wavelengths. By dissecting this faint infrared glow, scientists can identify the precise molecules present on the surface. And with Quaoar, this data has revealed something beyond the expected water ice and tholins, faint, unusual emission lines that do not match any simple, common ices. These spectral whispers are the signature of a far more complex chemistry at work, potentially involving the very building blocks of life. These anomalous lines are like cryptic symbols in an alien alphabet. They suggest the presence of what scientists call complex organic molecules. This doesn't mean molecules associated with life as we know it, but rather carbon-based compounds that are more intricate than simple methane or carbon dioxide. We might be seeing the spectral signatures of things like polycyclic aromatic hydrocarbons, or PAR, which are large, stable molecules made of interconnected rings of carbon atoms, often compared to tiny flakes of soot. Or perhaps we are detecting hints of molecules like ethane, ethylene, or even acetylene, which are more complex hydrocarbons than methane. On Earth, these compounds are often associated with industrial processes or combustion, but in the deep freeze of space, they form through non-biological chemistry, typically when simpler ices are zapped by radiation. The presence of such molecules would indicate that Quaoar's surface is an active cosmic laboratory, where billion-year-long chemical reactions are slowly building complexity from simple ingredients. The immediate question is, how are these complex molecules forming in such a hostile environment? The primary engine is almost certainly radiation chemistry. Quaoar's surface is constantly bombarded by galactic cosmic rays, high-energy particles racing across the universe, and by the faint but persistent ultraviolet radiation from the sun. When these particles slam into a patch of frozen methane or nitrogen ice, they deliver a tremendous amount of energy, shattering the simple molecules into highly reactive fragments. These fragments, like carbon atoms and methyl groups, then scurry across the surface until they randomly collide and stick together, forming new, more complex arrangements. It's a slow, statistical game of atomic billiards, but over millions of years, the probability of forming larger molecules increases dramatically. The cold actually aids this process. At Quaoar's temperatures, molecules move very slowly, so when they do link up, they are less likely to be shaken apart again by thermal energy. The surface acts as a cryogenic catalyst, freezing these new compounds in place as soon as they form. Another fascinating possibility is that these complex organics are not being created on Quaoar, but are being delivered to it. The Kuiper Belt is constantly being dusted with microscopic particles from comets and interstellar space. These dust grains can be incredibly rich in complex organic material. When they gently settle on Quaoar's surface, they could be contributing their own chemical signatures to the overall mix. However, the unique pattern of the emission lines suggests these molecules are being produced in situ, tailored by Quaoar's specific environment of ices and radiation dosage. The most profound implication of these strange infrared signals is that they might represent the precursors to probiotic chemistry, the chemical steps that, on the early Earth, eventually led to the emergence of life. The molecules we might be detecting on Quaoar are of the same class that, in a warmer, wetter environment, could undergo further reactions to form amino acids and nucleobases, the fundamental components of proteins and DNA. Quaoar itself is far too cold for any life-like processes to begin. Its surface is a sterile, frozen desert, but its value is as a natural museum, preserving in deep freeze the outcomes of the universe's innate drive toward chemical complexity. By studying these strange emissions, we are not looking for life, but for the pathways that make life possible. Quaoar becomes a reference point, showing us what kind of organic chemistry can proceed with nothing more than ice, time, and radiation. This transforms our view of the outer solar system from a barren wasteland into a repository of potential, suggesting that the raw ingredients for biology are being cooked up wherever the conditions are right, even in the most remote and unforgiving corners of a planetary system. The gravitational reach of a world extends far beyond its immediate vicinity, creating a subtle web of influence that can betray its presence and its properties. For our 20th mystery, we turn from Quaoar itself to the empty space around it, asking a deceptively simple question: has Quaoar's gravity left a fingerprint on its cosmic neighborhood? By meticulously tracking the paths of smaller, fainter Kuiper Belt objects that pass relatively close to it, astronomers can perform a form of celestial detective work, searching for the tiny, telltale wobbles that would reveal Quaoar's unseen hand at work. This technique, known as gravitational perturbation analysis, is one of the most powerful tools in astronomy. It's how Neptune was discovered in the 19th century, not by direct observation, but by its gravitational effect on the orbit of Uranus. In the vast, dark expanse of the Kuiper Belt, applying this same principle is exponentially more challenging. The objects are incredibly faint, their orbits are measured over decades or even centuries, and the gravitational nudges from a mid-sized world like Quaoar would be minuscule. However, with increasingly precise telescopes and decades of accumulated data, it is becoming possible to search for these whispers of gravity. The primary goal is to refine our understanding of Quaoar's mass. While we have a good estimate from the orbit of its moon, Quaoar, observing how Quaoar tugs on other, independent bodies provides a crucial cross-check. A more precise mass measurement would tighten our calculations of its density, offering even greater confidence about the size of its rocky core and the potential for internal oceans. Any discrepancy between the mass inferred from Quaoar and the mass inferred from its influence on other objects would itself be a major clue, potentially pointing to an error in our models or, more excitingly, to the presence of something we haven't accounted for. This leads to the most thrilling possibility embedded in this mystery: the potential to discover hidden companions. If astronomers detect gravitational perturbations on neighboring small bodies that cannot be explained by Quaoar's mass alone, it would strongly suggest the existence of other substantial objects within its gravitational domain. This could be the long-theorized second moon, too small and dark to see directly, whose additional gravity is subtly altering the paths of passers-by. Alternatively, Quaoar might even have a hidden Trojan population, small asteroids or moonlets orbiting at stable points 60 degrees ahead of or behind it in its path around the Sun, much like the Trojan asteroids that accompany Jupiter. The collective gravity of a swarm of such hidden objects, each individually invisible, could combine to create a detectable gravitational anomaly. Finding evidence of this would transform our view of the Quaoar system from a simple dwarf planet and moon duo into a complex mini-system, a bustling headquarters in the Kuiper Belt with its own entourage of smaller followers. Successfully detecting these perturbations would also provide profound insights into the population and distribution of material in this specific region of the Kuiper Belt. If Quaoar's gravity has clearly shepherded or disturbed a number of smaller objects, it tells us that there is a significant population of these smaller bodies in its vicinity. This, in turn, helps us map the density of the Kuiper Belt itself, revealing whether it is a uniform field of debris or has clumps and clusters shaped by the gravity of the larger dwarf planets. Conversely, a surprising lack of perturbation could be equally revealing. If, after a thorough search, no gravitational influence is found on nearby objects, it might indicate that Quaoar's region is unusually empty, perhaps cleared out by its own gravity in the distant past or never having been densely populated to begin with. This gravitational detective story is therefore about much more than just Quaoar. It is a probe into the structure and history of the entire trans-Neptunian frontier, using the dwarf planet's invisible pull as a measuring stick for the cosmos around it. The surface of a world like Quaoar is not a static canvas. It is a document constantly being rewritten by the harsh environment of space, and this brings us to our 21st mystery, a profound conflict between age and appearance known as the cosmic ray weathering paradox. Over the 4.5 billion years of the solar system's existence, the surface of any object in the Kuiper Belt should have been thoroughly processed or space-weathered into a uniform, dark, reddened state. This is the inevitable result of a relentless bombardment by high-energy cosmic rays and solar ultraviolet radiation, which slowly but surely breaks apart simple ices and reassembles them into complex, dark organic compounds called tholins. It's a process of cosmic aging, and Quaoar, by all rights, should look its age, a uniformly ancient, dark and cratered relic, yet as we've seen, it doesn't. The presence of those inexplicably bright, reflective patches creates a glaring contradiction. How can a surface be both 4 billion years old and look strikingly young? This paradox forces us to reconsider the very nature of time and change on these distant worlds. Cosmic ray weathering is an inexorable, if slow, process. Think of it like the sun fading a colored fabric left in a window. Leave it for a day and you might not notice. Leave it for decades and the change is dramatic and uniform. On Quaoar, the fabric of its surface ice has been sitting in the cosmic equivalent of a sunny window for the entire history of the solar system. The radiation dosage it has received is staggering. This radiation doesn't just darken the surface, it fundamentally alters the physical structure of the water ice itself. Over immense timescales, the radiation can disrupt the orderly crystalline lattice of water ice, turning it into amorphous ice, a glassy, disordered solid that has a different spectral signature. The fact that we still see evidence of crystalline ice on Quaoar is in itself a sign that the weathering process has been interrupted or countered by some renewing force. So, why do some areas seem to have resisted this universal darkening? The answer cannot be that these patches have simply avoided being hit. The bombardment of cosmic rays is isotropic, meaning it comes from all directions, bathing the entire world evenly. The difference must lie in the surface material itself, or in events that have reset the geological clock in specific locations. One compelling explanation is that the bright areas are simply newer. They are composed of fresh ice that has been recently exposed to the surface, whether through cryovolcanic activity, tectonic resurfacing, or a recent impact. This new ice has not yet had enough time to accumulate a significant dose of radiation. The dark patches, in contrast, represent the default state of Quaoar, the ancient, weathered terrain that has endured the full brunt of cosmic weather. This creates a world with a dual personality, part ancient archive and part dynamic landscape. The rate of this weathering is not a fixed constant. It can be influenced by local conditions. For instance, a surface covered in a thick, fluffy layer of porous ice might weather differently than a solid, compacted layer of ice. The porous material could trap the darkening agents more effectively, or it might allow radiation to penetrate more deeply but with less effect per volume. Furthermore, the specific mix of original ices plays a role. If Quaoar's bright patches are rich in very volatile ices like nitrogen or carbon monoxide, these ices might sublimate away at a faster rate than the darkening tholins can form, effectively keeping the surface bright by constantly turning over. It's a race between darkening and removal, and in certain spots the removal might be winning. The cosmic ray weathering paradox is therefore not just a simple puzzle with one solution. It is a dynamic interplay between a universal, aging process and local, rejuvenating events, a testament to the fact that even in the deepest freeze, change is the only constant. But even as we delve into the complex chemistry of its surface, we face a more fundamental problem, one that lies at the very heart of how we measure this distant world. Our 22nd mystery is a puzzle of basic dimensions. Why can't we agree on how big Quaoar actually is? You might think that determining the size of a solid object in space would be a straightforward task, but for a distant, faint world like Quaoar, it is anything but. Different observation techniques have yielded slightly different estimates for its diameter, and these small discrepancies are not just minor technicalities. They create a cascade of uncertainty that impacts our entire understanding of Quaoar's density, its composition, and even its fundamental nature. The primary methods for measuring a Kuiper Belt object's size are stellar occultations, thermal measurements, and direct imaging with the most powerful telescopes like Hubble or the James Webb Space Telescope. Each technique has its own strengths and inherent weaknesses, and for Quaoar, they seem to be telling slightly different stories. The most precise method is the stellar occultation, the same technique that revealed its impossible ring. As Quaoar passes in front of a distant star, the star's light winks out for a precise amount of time. Since we know Quaoar's distance from Earth and its speed along its orbit, the duration of the occultation allows astronomers to calculate its diameter with remarkable accuracy, often to within a few kilometers. This method gives a very reliable measurement of the object's apparent size at that exact moment. However, thermal measurements introduce a fascinating complication. Telescopes like the Herschel Space Observatory and the Spitzer Space Telescope have measured the total amount of heat Quaoar radiates into space. By combining this thermal flux with an estimate of its surface brightness or albedo, scientists can work backwards to calculate its size. A larger, darker object can emit the same amount of heat as a smaller, brighter one. This is where the uncertainty creeps in. If we assume Quaoar is very dark, like most Kuiper Belt objects, the thermal data suggests a larger diameter to account for all the heat we're detecting. But if it has brighter patches, as we know it does, the calculated size would be smaller. This intrinsic ambiguity means the thermal diameter is not a direct measurement but an inference that depends on another uncertain property, its average surface reflectivity. Direct imaging, while providing our only visual glimpse of Quaoar as more than a point of light, is also limited. Even with the phenomenal resolution of the Hubble Space Telescope, Quaoar appears as a tiny, blurry blob just a few pixels across. Measuring its diameter from this involves complex computer modeling to determine the best fit size for that smudge of light. This method is highly sensitive to the assumed shape of the object. If Quaoar is not a perfect sphere, but the model assumes it is, the resulting diameter will be an average that might not reflect its true dimensions. Given its irregular shape suggested by its light curve, this is a significant source of potential error. The consequence of these discrepancies is far greater than a simple debate over a few dozen kilometers. The size measurement is half of the equation needed to calculate Quaoar's density, which is the key to unlocking its interior. Density is mass divided by volume, and we have a relatively good handle on Quaoar's mass from the orbit of its moon, Quaoar. But volume depends on the cube of the radius. A seemingly small difference in the measured diameter can lead to a substantial change in the calculated volume, and therefore a significant shift in density. If one technique suggests a diameter of 1,100 kilometers and another suggests 1,170 kilometers, the resulting density estimates could differ by 10 or 15%. This uncertainty ripples through every theory we have about Quaoar. A higher density resulting from a smaller measured size would reinforce the idea of a massive rocky core, strengthening the case for internal heating and a potential subsurface ocean. A lower density from a larger size estimate would suggest a greater proportion of ice and a more porous rubble pile structure, making significant geological activity less likely. The ongoing effort to pin down Quaoar's exact size is not just an academic exercise in precision. It is a fundamental step in determining whether this distant world is a dense, complex geological entity or a lighter, more primitive amalgamation of ice and rock. Until we can reconcile these measurements, the very foundation of our understanding of Quaoar remains on slightly shaky ground. A reminder of the immense challenge of studying pinpricks of light at the very edge of our vision. Sometimes the most profound mysteries are not just physical but symbolic, woven into the very name we assign to a world. Our 23rd mystery takes us on a brief but fascinating detour from hard science to the realm of mythology, to the origin of the name Quaoar itself. Unlike many celestial bodies named after figures from Greco-Roman myths, Quaoar draws its identity from the rich cosmology of the Tongva people, the original inhabitants of the region around Los Angeles, where the dwarf planet was discovered at the Palomar Observatory. In their tradition, Quaoar is a great creator deity, a divine force who arrives in the primordial void and through dance and song brings the other gods, the sky, the earth, and finally, humanity into existence. This is not a name chosen at random. It is deeply resonant, imbuing this distant speck of ice and rock with a powerful thematic significance that eerily mirrors its scientific importance. When astronomers choose a name, they often seek one that reflects the nature of the object. In naming this world Quaoar, they unknowingly selected a moniker that would grow in relevance with each new discovery. Just as the mythological Quaoar is a creator who establishes cosmic order, the dwarf planet Quaoar is in a very real sense a creator of scientific puzzles. It has brought forth a cascade of new questions and challenges to our established order of planetary science, forcing us to recreate our models and our understanding of how ring systems form, how small worlds retain heat, and what processes shape the outer solar system. Each enigma we uncover is like a new entity summoned into being by this cosmic dancer, challenging our complacency and pushing the boundaries of human knowledge. Furthermore, the mythological Quaoar is a primordial being present at the very beginning of existence. This connects beautifully to one of the most compelling scientific hypotheses about the dwarf planet, that it may be a primordial object, a pristine relic from the dawn of our planetary system. Its placid orbit suggests it has been a peaceful hermit, avoiding the gravitational turmoil that reshaped so many of its neighbors. If this is true, then Quaoar is a time capsule, a physical remnant of the solar system's birth. Studying it is like listening to an ancient song that has been humming softly in the darkness for 4.5 billion years. A song that can tell us about the original ingredients and conditions from which our entire cosmic neighborhood was built. The name, therefore, is not just a label, it is a prophetic clue. It frames Quaoar not as a mere frozen rock, but as a foundational entity, a creator world whose secrets are fundamental to the story of our own origins. This intertwining of ancient myth and cutting-edge science adds a layer of profound depth to our quest, reminding us that our drive to understand the cosmos is itself a form of creation, a continuous effort to bring order and meaning to the vast and mysterious universe we inhabit. Before the New Horizons spacecraft performed its historic flyby of Pluto in 2015, The outer solar system was a canvas onto which we could project our best guesses. Based on the limited data from Earth-based telescopes, planetary scientists developed models of what a typical mid-sized Kuiper Belt object like Quaoar should be. These pre-Pluto predictions were logical, based on principles we understood from studying asteroids and moons closer to home. Yet, the reality revealed by New Horizons at Pluto, and subsequently reinforced by the intense study of Quaoar, was so different that it rendered many of those textbooks instantly obsolete. The 24th great mystery of Quaoar is this stunning chasm between what we thought we knew and what we actually found. A story of scientific humility that demonstrates how this distant world has been a consistent agent of surprise. One of the most dramatic miscalculations centered on the very nature of these worlds' surfaces. The pre-New Horizons model painted a picture of a uniformly ancient, dark, and heavily cratered landscape. The reasoning was sound, with no significant internal heat source and temperatures near absolute zero. Geological activity should be impossible. These were expected to be the most inert and unchanging places in the solar system, their surfaces preserving a perfect record of bombardment from the last 4 billion years. They were seen as cosmic fossils frozen in time. The reality, as we now know, is anything but. The discovery of Quaoar's bright patches and Pluto's even more stunningly complex geology, with its towering water ice mountains, vast nitrogen ice glaciers, and lack of widespread craters, shattered this assumption. Instead of a dead rock, we found evidence that Quaoar, like Pluto, possesses enough internal vitality to remake its own face. Scientists were completely wrong about the level of geological activity, forcing a fundamental rethink of how small, icy worlds generate and retain heat. This directly leads to a second major area where prediction failed: the expectation of a simple, undifferentiated interior. The conventional wisdom suggested that objects in the Kuiper Belt were relatively homogeneous mixtures of ice and rock. They were thought to be like giant, frozen dirt balls, with their material never having undergone the planetary scale sorting process known as differentiation, where heavy elements sink to the core and lighter ices rise to form a mantle. This was considered a privilege reserved for much larger, warmer planets. Quaoar's unexpectedly high density was the first clue that this model was flawed. It forced the conclusion that Quaoar does, in fact, have a differentiated structure with a substantial rocky core. New Horizons data on Pluto confirmed this on a grander scale, showing clear evidence of a rocky core separated from an icy mantle and even a subsurface ocean. The prediction of simple, primitive interiors was another casualty of our encounter with reality, revealing that these distant dwarfs have complex, layered histories akin to true planets. Perhaps the most humbling miscalculation of all involves Quaoar's impossible ring. Before its discovery, our understanding of ring formation was neatly encapsulated by the Roche limit. This was a fundamental law of orbital mechanics, a rule that had held true for every ringed planet from Saturn to Neptune. The prediction for any object like Quaoar was clear. If it had a ring, it would be inside the Roche limit. If material existed outside that limit, it would quickly coalesce into a moon. The existence of a dense, narrow ring orbiting far beyond this gravitational boundary was not just a surprise, it was a violation of a rule we considered universal. This wasn't a case of being slightly off in a measurement. It was a fundamental challenge to a core principle of physics as applied to planetary systems. Where scientists predicted orderly behavior governed by well-understood laws, Quaoar presented a chaotic anomaly, a phenomenon that demanded the invention of entirely new concepts like the bouncing, fluffy particles or electrostatic repulsion to even begin to explain it. Even the expectations for atmospheres proved to be overly simplistic. While scientists knew that Pluto had a tenuous atmosphere, the general assumption was that smaller objects like Quaoar would be utterly airless, their gravity too weak to hold onto any gases. The prediction was for a stark, bare surface exposed directly to the vacuum of space. While Quaoar does appear to lack a significant atmosphere, the reasons are now understood to be far more nuanced than just weak gravity. The potential role of surface composition, a sealing layer of tholins or a porous subsurface that traps gases, adds layers of complexity we never anticipated. Furthermore, the discovery of hazy, complex atmospheres on Pluto, with multiple layers and a chemistry driven by the sublimation of surface ices, showed that even the atmospheres that do exist are far more dynamic and structured than the simple, uniform envelopes that were predicted. This grand disconnect between prediction and reality is more than just a list of scientific errors. It is a powerful lesson in the nature of exploration. Quaoar and its ambassador Pluto have taught us that the outer solar system is not a realm of simple, frozen relics following a predictable set of rules. It is a domain of bewildering complexity, where local conditions, unique histories, and physics we are only beginning to grasp create worlds of stunning individuality. Each time our models said Quaoar should behave one way, it defiantly chose another. It forced us to abandon our comfortable assumptions and embrace a more complex and ultimately more fascinating reality. This object has consistently acted as a cosmic corrector, pointing out the flaws in our theories and compelling us to dig deeper, to think more creatively, and to acknowledge that the universe is always more inventive than we are. And so we arrive at the final and perhaps most fundamental of Quaoar's 25 mysteries, a question that strikes at the very heart of its identity. What exactly is it? Is Quaoar truly a dwarf planet, or is it something else? This isn't merely a semantic debate. It's a classification crisis that encapsulates all the other puzzles we've explored, forcing us to confront the gap between our tidy definitions and the messy, complex reality of the cosmos. The official definition, as set by the International Astronomical Union, seems simple enough. To be considered a dwarf planet, an object must orbit the Sun. It must not have cleared the neighborhood around its orbit, and crucially, it must have sufficient mass for its own gravity to pull it into a state of hydrostatic equilibrium. This is the scientific term for being round. It's the threshold where an object stops being an irregular lump of rock and ice and becomes a miniature world, where gravity overcomes the material strength of its composition and molds it into a sphere. This is the line that separates asteroids and most Kuiper Belt objects from the planetary big leagues, even the dwarf variety. For many objects, this is a straightforward call. Pluto, Eris, Haumea, they are clearly round. A small asteroid is clearly not, but Quaoar sits right on the precipice in a frustrating and fascinating zone of ambiguity. The evidence for Quaoar's roundness is compelling but indirect. Its rapid rotation strongly suggests that it has achieved hydrostatic equilibrium, at least in a distorted form. As we discussed, that fast spin should have sculpted it into an oblate spheroid, a squashed sphere that is wider at the equator than at the poles. This is a form of equilibrium. It's the shape a fluid body would take when spinning, and many confirmed dwarf planets like Haumea are known to be oblate. Furthermore, the variations in its light curve, while indicating an irregular shape, still show a pattern consistent with a body that is fundamentally rounded by gravity, albeit with significant surface features or a large impact basin that creates bumps and dips in its profile. The calculated mass and density also support the idea that Quaoar has enough self-gravity to have pulled itself into a spherical shape during its formation. In many ways, the preponderance of the evidence points toward Quaoar having crossed that critical line. Yet, the case against its dwarf planet status is equally persuasive and hinges on that very same light curve data. The irregularities are not minor, they are pronounced, suggesting a shape that is far from a smooth ellipsoid. This raises a critical question. Has Quaoar fully achieved hydrostatic equilibrium, or has its gravity only partially succeeded? Perhaps it is what scientists call a rubble pile, a collection of fragments held together by gravity, but one that is not quite massive enough to fully overcome the friction and structural strength between those fragments to become perfectly round. It might be caught in a state of being mostly round, but with significant topographic extremes that a more massive world would have smoothed away. If a giant impact crater is responsible for the irregularity, that itself is evidence that the crust is strong enough to support such a feature without collapsing, which might not be the case on a more fluid, fully equilibrated body. This debate is more than academic. It reflects a deeper philosophical divide in how we classify the solar system. Is hydrostatic equilibrium a strict binary condition? You're either round or you're not. Or is it a spectrum, a gradual process that objects undergo as they grow in size? Quaoar might be the perfect example of an object in transition, a world that is actively demonstrating that nature doesn't always fit into our neatly labeled boxes. Its unresolved status is a testament to its unique position in the size gap, too complex to be a simple asteroid, yet not unambiguously conforming to the ideal of a dwarf planet. Ultimately, the mystery of Quaoar's classification may never be settled with absolute certainty from Earth-based observations alone. The final verdict will likely require a close-up visit from a spacecraft, which could precisely map its topography and measure its gravitational field to see if its shape truly matches what gravity alone would dictate. Until that day, Quaoar remains in a class of its own, the cosmic question mark at the edge of the solar system, challenging our definitions and reminding us that the most interesting things in the universe are often the ones that defy easy categorization. All these profound mysteries, the impossible ring, the hidden ocean, the puzzling composition, point toward an undeniable truth. To truly understand Quaoar, we must go there. The tantalizing clues gathered from across 4.5 billion kilometers are like reading a fascinating novel by observing the flickering shadow it casts on a wall. We can infer a great story, but we yearn to open the book and read the words directly. The future of Quaoar exploration hinges on taking that next great leap, moving from remote observation to direct encounter, and the technologies taking shape today promise to make that a reality within our lifetimes. The next era of discovery will be driven by two powerful forces: advanced telescopes that will scrutinize Quaoar with unprecedented clarity from Earth's vicinity, and ambitious spacecraft that will journey into the deep freeze for a rendezvous with the dwarf planet itself. From the comfort of our own planet, a new generation of observatories is set to revolutionize our view of the Kuiper Belt. The Vera C. Rubin Observatory, scheduled to begin its legacy survey of space and time in the coming years, will be a game-changer. This monumental project will not find Quaoar. We already know where it is, but it will scan the entire sky with a relentless, all-seeing eye night after night for a decade. This will allow astronomers to track Quaoar's brightness with a precision never before possible, refining its light curve to an exquisite degree. We will be able to map its rotational irregularities in minute detail, potentially confirming the existence of that giant impact basin or the gravitational tug of a hidden moon by detecting subtle, repeating patterns in its flicker. Furthermore, Rubin's vast survey will likely discover hundreds of new Kuiper Belt objects, many of which will share orbital characteristics with Quaoar. By finding these dynamical siblings, we could finally confirm or refute its connection to the Haumea family, placing Quaoar within a broader genealogical tree of the outer solar system. But even Rubin's powerful gaze has its limits. To pierce the chemical secrets of Quaoar's surface, we look to the successors of the James Webb Space Telescope. Future flagship observatories, designed with even larger mirrors and more sensitive infrared spectrometers, will be able to dissect Quaoar's faint heat signature with the precision of a surgeon's scalpel. They won't just confirm the presence of water ice, they will map the distribution of different ices across its surface, identifying the exact locations of those mysterious bright patches and analyzing their unique chemical fingerprints. The strange emission lines hinting at complex organics will be resolved into definitive spectral signatures, telling us exactly which carbon-based molecules are present and in what quantities. This could provide the smoking gun for ongoing chemical evolution, showing us the building blocks of prebiotic chemistry being assembled in real time on a frozen world. These telescopes will act as remote laboratories, allowing us to conduct a preliminary analysis of Quaoar's surface from afar, guiding the design of future missions with pinpoint accuracy. However, remote sensing, no matter how advanced, can only tell us so much. To solve the deepest mysteries, to probe for that subsurface ocean, to scoop up a sample of the ring particles, to feel the texture of its surface, we need to send a visitor. The most ambitious and transformative future for Quaoar science lies in a dedicated flyby or orbital mission. Imagine a spacecraft, a descendant of the brilliant New Horizons probe, designed specifically for the Kuiper Belt. After a swift journey powered by advanced propulsion, it would begin its approach, its cameras resolving Quaoar from a distant speck into a world. We would finally see its true shape, a bizarre amalgamation of a gravitational sphere distorted by rotation and scarred by impact. High-resolution maps would reveal the nature of the bright and dark terrain, showing us whether we are looking at cryovolcanic flows, tectonic fractures, or vast fields of seasonal frost. The scientific payoff would be monumental. A radio science experiment would precisely measure Quaoar's gravitational field by tracking the slightest wobbles in the spacecraft's path. This data would be the definitive test for a subsurface ocean. If the icy crust is decoupled from the core by a liquid layer, the gravity signature would be unmistakable. A dust analyzer could fly through the region of the ring, directly sampling the particles to determine their size, density, and composition. Are they fluffy snowballs or hard ice chunks? This single measurement could solve the mystery of the ring's stability overnight. And if the spacecraft carried a mass spectrometer, it could even attempt to fly through any potential cryovolcanic plumes, tasting the chemistry of Quaoar's hidden interior and searching for the complex organic molecules that are the precursors to life. Such a mission would transform Quaoar from a subject of speculation into a known world, a place with a definitive history and a clear place in the solar system story. The journey to reach Quaoar within a reasonable time frame will likely require new technologies, and here the future gets even more exciting. Solar sail propulsion, which harnesses the gentle but constant pressure of sunlight, or next-generation ion engines could enable faster, more agile missions to the outer solar system. Nuclear propulsion, a concept being revisited by space agencies, could dramatically cut travel times, sending a probe to the Kuiper Belt in years rather than decades. These are not science fiction dreams, they are active areas of research that could mature just as the scientific case for a Quaoar mission reaches its peak. The path forward is clear. We will use our ever-sharpening eyes from Earth to pick our targets, and then we will build the ships to visit them. The next chapter in the story of Quaoar will not be written by astronomers watching a flickering star, but by a robotic ambassador sending back a torrent of data, revealing this cosmic rebel in all its glorious, mysterious detail. The greatest discoveries about this distant world are not behind us. They are waiting in the future, just over the horizon of our current technology, beckoning us to explore. From the impossible ring that orbits in defiance of gravity to the profound silence where an atmosphere should whisper, from the enigmatic bright spots hinting at a warm heart to the deep uncertainty about its very shape and status, Quaoar has proven to be a world of relentless paradox. Each of these 25 mysteries is not an isolated puzzle but a thread in a single, magnificent tapestry, one that depicts a solar system far more complex, dynamic, and surprising than we ever dreamed. Quaoar is more than just a distant dwarf planet. It is a keystone, a Rosetta Stone for deciphering the history and physics of the entire trans-Neptunian realm. Its placid orbit suggests it may be a pristine relic of the solar system's birth, while its violent spin and potential for internal oceans scream of a world that is geologically alive. It challenges the rigid laws we derived from the planets closer to the Sun, forcing us to invent new physics to explain its bizarre ring and to reconsider the very definition of a world. It stands in the critical size gap, teaching us that geological vitality is not a binary switch but a dimmer, active even on modest worlds in the deep freeze. The story of Quaoar is the story of scientific humility, a constant reminder that for every rule we write, the universe holds a defiant exception. The journey to understand this cosmic rebel is far from over. It is a story still being written by astronomers pointing ever more powerful telescopes toward the void, and by engineers designing the spacecraft that will one day visit this enigmatic world. The greatest chapters of discovery are yet to come, and this is the true lesson of Quaoar. It is an invitation to remain curious, to look up at the night sky not as a static canvas of twinkling lights, but as a dynamic, evolving frontier. Every faint point of light holds a story, a set of mysteries waiting for the next generation of explorers to unravel. So the next time you find yourself under a clear, dark sky, remember that out there, in the perpetual twilight beyond Neptune, a small world named Quaoar is silently rewriting the textbooks, daring us to dream bigger and question deeper. The cosmos is calling. Stay curious, follow the journey, and never stop.